Hi everyone, how is everyone doing? This is going to be a unusual video for this channel because actually the episode 2 did not work out really well because of some technical issues and which unfortunately I did not manage to prevent. So I decided to just do a little extra for you guys because I don't want to just leave a video that has so many frames lost, and I still want to deliver and do something interesting. So as an exception, it is going to be a sort of bonus content for the episode 2. I'm just going to basically go through all the things again. Um, Unfortunately, there won't be any chat because I'm not going live right now. But maybe it can still be fun. So let's just try it. So yeah. So in the second episode, we planned to go through the quantum operators, and today we can just do it again, and can still be interesting. So, but before we actually do anything with the operators, in the episode 1, I did a little mistake, and I think I would like to correct myself. Let me just bring back the appropriate file here. So, as you may or may not remember, there was a problem comparing complex numbers to the real numbers. So I just assumed that if the complex number is 0, Python would treat it as real. But of course it's not the case because, in programming everything is governed by types, and if it's a complex type and there is no operator defined to compare it with a real type, it just wouldn't work. So yeah, and that was not maybe the best way to compare what I wanted to compare. So today I'm just going to fix that thing really fast and introduce you the concept of fidelity. So let's just add one more test here. Test fidelity on the plus state. So fidelity is a probability of measuring the state that we intend to measure, more or less. That's at least how I define it and how I understand it, and that's why it's good to introduce it right now because we will need it when we simulate measurement, which is what we planned for later anyway. So fidelity is we already introduced overlaps, and for fidelity we will need absolute value squared of the overlap. So for example, we have a plus state, quantum state plus, and we want to know the probability of measuring 0. So we take overlap with 0, and take the absolute value squared of that overlap. And this is the fidelity of 0. And we can also do it with 1. So we already know how to compute the overlaps using QuTip. So allow me to take the absolute value squared of this overlap. So numpy apps squared, and inside of that we put the appropriate overlap. So this is overlap of 0 with overlap with plus, and same thing we do for the other one. So this is overlap with 1, and it's going to be the same except that we put 1 here. And we would accept both of those, we would expect both of those values to be close to, I mean, to be 1/2 exactly, but in numerics, we don't actually compare exactly the floating point numbers. So for that purpose, we can use numpy function is close. Numpy is close. So P0 and P1, both, we expect both of them to be 1/2, right? 0.5, 0.5. And this thing returns a list of booleans. So this should be true, true. But we want all of them to be true. So all. Okay. That's the thing. Let's just run it and see. So PyTest solutions, that was episode 001.py. BEA beautiful. For past. Let's just do it in verbose to see a list. Nice. Yeah, fidelity plus past. Okay, so that's the fidelity. And just leave the episode 1 for now. And let's get back to the episode 2, which is what I recorded 2 days ago. But the recording is not good, so I will just go through it again for you guys. And let's just have some fun. So today we're going to talk about quantum operators. The challenge I propose is define few single qubit and multi-qubit quantum operators. Test if they act on the states as expected, including the case of their eigenstates. Automate your test. Okay, so we already talked about states, but in order to start talking about operators, we have to sort of get more intuition about what quantum states actually are. So classical states, in a computer is basically a big, I mean, it's a small machine with many switches that get turned on and off. So these are zeros and ones, but they can be only like either 0, either 1. They cannot be both at the same time. And those are the classical bits. In case of qubits, the space of values of solutions to a qubit is known as the Hilbert space. It can be visualized in form of sphere, like you can see on this figure, which is called the Bloch sphere. So there is the 0 state on top and the 1 state on bottom. So these are the ones we are familiar with. There's also a plus state, which is next to the X. And the operators, what are the operators? Classically, operators are something that can change 0 into 1, like classical gates. In quantum, operators are also just something that changes the quantum state. So as you can deduce from the name, operators operate on something, right? So in the simplest sort of words, for this example, operators would basically move points on this Bloch sphere. So yeah, but this picture is quite tedious and not everyone might be very familiar with this kind of notation. So for you guys, I prepared an alternative representation. So instead of Bloch sphere, I will use the bold sphere, which is equivalent to the Bloch sphere. But every sort of how to say, every recognizable point orthogonal point on the Bloch sphere here has a pictorial representation, and the zero state is the bald guy. So everything sort of boils down to how your head sort of looks like, and the guy on top, the zero state, is the bald guy. The guy on bottom, the one state, is the ninja guy. I'll explain you why it is a ninja later. And other states on this plane around are basically different hair colors. So the z operator rotates about z on the sphere, and could be interpreted as the hair dye operator, so it can change your color. So if you rotate about z, the redhead guy, which is plus I, by angle like pi over 2, you will get a gray hair guy. Like if you do it again, you will get a blonde hair guy, etc., etc. And there could be other operators which also that could change the bald guy into brown hair guy. Like so many bald guys would really love to have such operator. And there's also this ninja guy. So the reason why he is a ninja guy is I need an example to explain for you guys the concept of the eigenstates. So eigenstates are sort of special states with respect to an operator which do not really get affected by the operator. So let me explain. If you apply the hair dye to the blonde guy, his color will change, so the state will change, right? So in quantum, that would mean that, not even in quantum, in linear algebra, that would mean that the blonde guy is the eigenstate of is not the eigenstate of the hair dye operator. On the other hand, if you apply hair dye to the bald guy, he will still be a bald guy, right? And same goes to ninja. I mean, if you just put hair dye on him, maybe his hair color would change, I don't know, but nevertheless, you won't be able to observe that, right? So let's just say that the ninja is also an eigenstate of the hair dye operator. And other operators that do other things to those dudes on the sphere also have their eigenstates. It's just more tedious to maybe find the interpretation of those operators, but if you have some ideas, feel free to let me know in the comments. We can iterate and maybe improve the bold sphere in the future. So in today's episode we are going to basically act on those dudes here and change the quantum state using the operators. But before we do so, allow me to provide you one more analogy to what the eigenstates are. So that's actually my favorite analogy, the Groundhog Day analogy. So I don't know if you guys have seen the Groundhog Day. This is a movie with the great Bill Murray. By the way, Bill Murray, you're the best if you're watching this. And so in this movie, Bill Murray, he's the weather reporter, and he visits this town when they have this weird tradition about the groundhog predicting the weather, etc., etc. But the thing is, he really hates it. He hates this trip, but unfortunately, he gets stuck in some sort of time loop. So every day he wakes up in the hotel, he lives exactly the same day. He just cannot get out of this town, And he tries to sort of do different things, and he learns everything about this town. Like every day he tries to do something else, but it's still the same day. Next day he wakes up, it's still the same day. Everything is the same, always the same. So you could say that if Bill Murray is an operator, he operates, on the world around him, and the world around him is the quantum state. Then in this movie, Bill Murray is just stuck in his eigenstate. Whatever he does, the state is the same. I mean, there is something happening because he does different things and he learns something, etc. So there is some eigenvalue that could be pulled out during this, but nevertheless, next day is still the same day. So yeah, that was another analogy for this thing. But enough of the analogies, and let's maybe do some coding. So, okay, well, I always start the same way, import numpy as in p. There's really nothing I do without numpy in my life. Yeah, a few more years like this and I will just, open the refrigerator with numpy and cook with numpy, and that was a bad joke. It's way more fun to do it when there's someone in the chat. I miss you guys already, and I miss Bill Murray also. Okay, so what do we need from QuTip? I'm getting distracted. We are going to work with states, so we need bases. We will also we're going to do something multi-qubit as well, so we will need tensor product, and we need operators. Just as I said, just to rotate those states, we will need to have operators that rotate around about x, about y, and about z. Maybe also an identity operator. Yeah. By the way, if you want to read about this, because my explanation is really quite shitty, just Google Pauli operators. These are Pauli operators. Okay, well, let me just pull up the bold sphere. Bold sphere is here. We have the bold sphere. So my camera is just not very straight here. So yeah, let's make this bold guy state, which is the zero state. Guys, another advantage of using this, of this example, is actually I can show you that it doesn't really matter how you name your states, right? It could be called zero, it could be called bold guy, like whatever, who cares, doesn't matter. You can always remap names, rename things, and what matters is what it does, and that's it, just like in life. And okay, so I'm getting distracted again. The bold guy. Bold guy is the zero state in our convention. So bold guy state. And yeah, the ninja guy. Cat1 equals basis to 1. I don't know if I told you guys, my roommate's name is Ninja. It's pretty cool. Ninja guy state. Okay, I hope he doesn't think I talk about him. Okay, so we want, what do we want to do here? Let me pull up this. Test if they act on the states as expected, including the case of the eigenstates. Okay, so let's get back to the bold sphere. So, well, the bold guy is the eigenstate of the Herr-Die operator, which in quantum is 0, is the eigenstate of the sigma z operator. So from the previous episode, we know how to calculate the overlap. So we can test it using the overlap. So we want to check if maybe, so this is overlap 0 with 0, right? And we know from the previous episode that this is 1 because we tested it together. So if we put z inside of it, that should still be 1, assuming this creates 1. So this should be, will it be the same for the 1 state? Let me just write it first. Yeah, so for 0 it pulls out 1, for 1 it pulls out negative 1, so this will be negative 1. Okay, and what about different operators? So for different operator, let's say if we do 0, 0, and if we put something that is not eigenstate, something that 0 is not eigenstate of, so x for example, so that would be the operator that can turn you into a ninja. That just has to be 0. You know why? Because when we do this, like from here, he is no longer bald. So you cannot measure bald on someone who is no longer bald, because this operator changed him. Like that operator could not change them. Still a ninja, still bald. Like he tried so many things to stop being bald, didn't work. Overlap still 1. Here he did this and he's no longer bald. The overlap is 0. Okay, enough blah blah. Let's just okay, so assert. So we assert overlap 0. Okay, we want it to be 1. And here we act sigma z, sigma z 2 on cat 0. Okay, same here. I mean, not the same, it's different. Cat 1 overlap with sigma z acting on cat 1. We expect that to be negative 1. Here is our favorite case because it makes us stop being bald. Cat 0 overlap sigma x acting on still cat 0. We want that to be 0. Okay, you guys want to test it? Let's test it. Oh, let's write something in the end. Kawabanga. Anyone likes The Simpsons? If you like The Simpsons, write me in the comment. I don't have chat, but maybe I can get your message from the future. Okay, Python Solutions, episode 002, bang, boom. What do we have? We have Kawabanga, great, okay, that's perfect. So we tested the eigenstates. We tested the eigenstates of the bald sphere. Not all of them, of course, but some of them, and well, that's good enough. So what's next? Let me just my memory is just so short. I already forgot. Yeah, so we have to test if the states get as expected. So if I remember correctly, during the stream, which was not properly recorded, I think what we did was we have rotated bald guy into ninja guy. But did we do it using sigma x or sigma y? Whatever, I mean, who cares? So basically, so that would be equivalent of testing if so ninja has to be created from the bald guy by applying x or y. Let's say y. This should be 1. Okay, let's do it. No, overlap sigma x acting on ket 0. That's 1, not 21, it's 1. Okay, let's get back to our shell and run it again. Nice. Okay, Kawabanga. Good. That's perfect. And yeah, another thing I talked during the live stream, which is interesting to mention because that's purely quantum thing, which is so in quantum there exists something like the squared root of the operator. So there is really no proper analogy in classical because I mean there are analogies, but I don't think they're good because those are the analogies that would make sense in classical, but we need one that doesn't. So think about negation. You know, negation is an operator, right? Like, for example, I say that I don't know. I say that this beer is good, and someone tries it and say no, it's bad. This person has negated my statement. So negation is an operator. There is a negation gate, NOT gate, in the computer. That if you put 0, it will make it 1. If you put 1, it will make it 0, etc., etc. So it makes sense to make negation operator, but it doesn't make sense to half negate something classically, right? So you can turn 0 into 1, you can turn 1 into 0, but you can't half do it, right? Classically, it doesn't make any sense. But in quantum you can. In quantum you can do square root of y, square root of x. You can do even less than square root, like whatever, you can do it. In quantum it makes sense. So how about we make this square root operator, square root of x maybe, and let's apply it to so we can make, yeah, we can make, maybe we can make the plus state from 0 state. So we would go from the bald guy to the brown hair guy, because if we do, hold on, yeah, if we do x, it will become a ninja, but we want to do half of it, you know. So let's make plus state just to have something to compare. What was it? 1 over square root, right? You know, guys, I write 1 over square root of 2 so many times during the day that sometimes I want to write 2 and I just write square root of 2 instead. Okay. Plus, did I say plus? Yeah, I did say. So ket 0 plus ket 1. What's wrong with this space? And square root of x is going to be it's going to be 1 over square root of 2. Oh, actually I don't need this parentheses. Or do plus another 1 over square root of 2. I'm not going to explain why, but if you want to know, you can ask me on Twitter. Sigma x. Okay. Okay, well, briefly, it's because we like half do sigma x, half we don't do it. And it's 1 over square root of 2 because it has to be normalized to 1/2. Hope it makes sense, does it? How does it make sense? I think it makes sense. Okay. Actually, I don't need this extra parenthesis here. So I'm so paranoid over parentheses, guys. Even though it's not live, I'm still paranoid. Okay, so that should create the plus state, right? Plus. Maybe we can just do. Oops, sorry. Did I say I'm not good with Emacs? Still learning. God damn it. Why is it doing it? So annoying. Let's just do this. Let's just apply it. Stop doing that. So, guys, you guys are witnesses. Like, why is it doing that thing? It's so annoying. I'm glad I have it on tape because times cat 0 cat plus. Okay, let's pray. Let's pray. Let's pray. Yeah, so I did say previously that you're not supposed to exactly compare reals, but this is QuTip. QuTip does some magic there that makes it possible. What? Yeah, I knew it. There's problem with parentheses. I felt it, guys. I felt it. Okay. Moment of truth. Yep, we have Kawabanga. Great. Okay. Yes. What else? So let's see. Automate your test. Okay. Oh, multi-qubit. Yeah. We talked about CNOT gate. Yeah. So there is sort of very interesting gate called a controlled NOT gate, CNOT, such that, so this is like X, you know, it flips 0 into 1, but it depends on the another qubit. So one qubit is sort of a control qubit, and another one is the target qubit. So if you apply CNOT to 0, 0, you will get 0, 0. It's less spectacular than I anticipated. I wanted some suspense. Let's write all the outcomes of the CNOT. So 0, 0 will be 0, 0. 0, 1 will be 0, 1. But 1, 0 will become 1, 1 because the control qubit is 1. So it says, hey, flip the other one, and it flips it. And 1, 1 will become 1, 0 because the control qubit is 1, and it makes the CNOT gate flip the other one. So let's make this gate, it's going to be a 2-qubit gate. It's going to be a 2-qubit gate. Hold on, maybe let's write some definition first. So do you guys remember orthogonality? I think we tested last time. So we know that this is 0 and this is 1, right? So we can use this property to sort of turn this into this, but at the same time turn this into just nothing, just make it vanish. because that thing will be 0 here. So we can do that. We can multiply 0, 0 by identity operator, which does nothing, and then 1 times x. So if we supply it with something that is 0 on the first qubit, sorry, there's a tensor product here, just to clarify. So if we supply it with something that has 0 on the first qubit, it will end up in this subspace and it will only apply identity. But if there's 1, it will end up in this subspace and it will apply x on the second qubit. So we can make it, right? We can make it like this. Tensor. Remember the tensor? So cat0 times cat0 dot dagger identity plus another tensor. It's going to be cat1 times cat1 dagger times sigma x. No, not times. Tensor sigma x. Is that right? I think it is right. Let's make some states to test. Tensor 0, 1. Sorry, 1 0 tensor cat1 cat0 cat1 1 tensor cat1 cat1. Let's just test our properties. So yeah, maybe like this. CNOT times cat0 0 equal cat0 0. Just let's test one for now, because I have a feeling something might be wrong, because Murphy's law. It's actually fine, but okay, well, just a sanity check, because everything was fine until now, and that's just suspicious. No, fine, okay. See guys, I don't even trust myself. Okay, so the outcomes to test. Wait, here is all the outcomes: 0 0 0 1 1 0 1 1. So these stay the same because control qubit is 0, and these, the second one gets flipped. So that one is 1 1, and that one is 1 0. And if this is going to be Kawabanga, then we are awesome. Let's see. Great. Perfect. Okay, we got it. We got it, guys. We did it. We have everything. Let's just save it. Whoa. What did I... Okay, it's fine. I'm using different keyboard and keep confusing the keys. So let's just get back to the bald sphere. Just hopefully YouTube will use it as a thumbnail for the video. So yeah, that's it. So we did quantum operators today. Next time maybe simulation of measurements. You guys can let me know in the comments what you prefer. Thank you so much for watching. Thank you for subscribing. I really appreciate it. That's why I want to do a little extra for you guys. I just couldn't really stand the fact that the Saturday stream did not work out. but yeah, decided to be very mature about it and use it as an opportunity to do something for you guys. Yeah. What else? So, oh yeah, one more thing. Actually, I really want to recommend you this book. A little advertisement. It's written by Tim Byrnes and Ilo-Okeke. Quantum Atom Optics: Theory and Application to Quantum Technology. So yeah, this is a very nice textbook, quite advanced, to be honest, a bit too advanced for the kind of things we are doing now. But you can find some pretty interesting and useful things here, which are not always easy to find in other books. And it is a great book, and it deserves to be checked out. So I really recommend it. You should really give it a chance. And yeah, maybe you can check your school library if they have it. If they don't have it, you can request them to order it. Um, Otherwise, you can. I mean, if you really want, you can find it on the internet. Uh, I'm not encouraging piracy or anything. But I will also include a link to Cambridge University Press if you want to order, in the description of this video. And yeah, that's it. Thank you for watching, and sorry again for the Saturday stream. Hopefully next time it can be better. Stay safe. Bye. Cheers.